Welcome back to the deep dive. We are pulling up a chair today for a really deep technical exploration of something critical but often invisible in cloud infrastructure, the rate limiter.
It really is. It's like the essential traffic cop of the internet, isn't it? If you, the listener, have ever wondered how these massive services, think social media, cloud platforms, huge e-commerce sites, how they handle just billions of requests all at once without, falling over from resource starvation.
Yeah.
Well, the rate limiter is pretty much the core answer. It's
Right.
this highly optimized gatekeeper. Its job is basically controlling the flow, limiting how many requests a client can make in a certain time, and crucially, blocking the extra ones before they hit your main servers.
Okay, yeah, let's unpack this because it sounds like a huge design challenge. Our mission today really is to give you a shortcut to understanding the whole system design, everything you need to think about to build a flexible, scalable server-side API rate limiter.
Definitely.
And when we talk about controlling requests, it's easy to stay abstract. But what does this actually look like? Like in the rules?
Yeah, good question. We're talking about really specific, concrete rules. Things tailored to user behavior or resource use. So, for instance, a content platform might say, okay, a user can't write more than, say, 2 posts per second. That's a speed limit, mostly for stability.
Okay, makes sense. And then you have rules more for security.
Exactly.
Yeah.
If you're dealing with account creation or logins, maybe you restrict based on where the request is coming from. Like you might only allow a maximum of 10 new accounts per day from the same IP address. That's to stop bots just mass registering.
Right, the bot problem.
Or, in gaming or e-commerce, maybe for claiming rewards, you might have a limit spread out more. Like you only claim a reward 5 times a week from the same device.
Yeah.
Stops people abusing the system. They seem simple on the surface, these rules.
Yeah.
But building the system to enforce them globally at scale, that's where it gets complex.
Okay, so before we dive into the how, let's nail down the why, because I think the first thought is just, oh, it stops bad guys. But the benefits seem much broader than just security.
They absolutely are. Yeah, the first one, the obvious one, is security and stability. Rate limiting is your main defense against denial of service, DOS attacks, both the deliberate ones trying to crash you and the unintentional ones. Like a buggy client stuck in a retry loop or just bad code sending floods of traffic. Either way, it leads to resource starvation, brings things down.
I was looking at some examples, and these aren't just theoretical limits, are they? They're really keeping huge services online, like Twitter limiting tweets to 300 every 3 hours.
Right. Or Google Docs, I think, has a default limit, something like 300 read requests per user every minute for its APIs. If your app goes over that, boom, it stops working for a bit.
And that directly ties into the second big benefit you mentioned, cost control, which I guess isn't always obvious.
It's often overlooked, but yeah, imagine you're a developer, your app uses third-party APIs that you pay for per call, like checking credit scores, making payments, pulling health records.
Yeah.
If your code has a bug, maybe it goes wild and makes 1,000 unnecessary calls, well, the rate limiter on their end acts like your financial safety net. It stops you racking up a massive bill because of a mistake.
So throttling isn't just about keeping the servers happy, it's literally about the bottom line sometimes.
Exactly. And the third benefit is just pure preventing overload. Even if the traffic isn't malicious and it's not costing you per call, just filtering out excessive requests, maybe from badly behaved clients or simple web scrapers, it reduces the load on your actual API servers.
Right.
Lets them focus their, CTU cycles on processing the real valuable traffic instead of just constantly saying, nope, you're blocked.
Okay, that makes the why really clear. So let's define what we're actually trying to build here. What's the scope? This needs to be robust, right?
Absolutely. We're designing a server-side API rate limiter. That's key server-side.
Yeah.
And it needs to be flexible. It has to support different kinds of rules throttling based on IP address, user ID, maybe an API key, or, other properties we might define.
And it needs to handle tons of requests, right? Scale is a big factor.
A huge factor. It must handle a large number of requests and operate correctly in a distributed environment. That immediately brings in complexity around things like consistency and synchronization.
And then there were the non-functional requirements, the things that make it actually good.
Yes, exactly. We need low latency. The check itself can't add noticeable delay to the API response. That defeats the purpose.
Right.
We need minimum memory usage, especially crucial if you're tracking limits for millions or billions of users or entities. Memory gets expensive fast. It needs high fault tolerance. Meaning, if one part of the rate limiter system has a problem, it shouldn't bring down your entire API. The system needs to degrade gracefully or have redundancy.
Okay.
And finally, it needs clear exceptions. You can't just drop requests silently. You have to tell the client, hey, you're throttled,
Mhm.
usually with that 429 status code we mentioned. And critically, tell them when they can try again.
Balancing all of that flexibility, scale, performance, cost, reliability, that's the real challenge here.
That's the entire design process in a nutshell. It's all trade-offs.
So, first big architectural decision, placement. Where does this check actually happen? I mean, instinctively you might think, why not put the logic on the client, like in the browser or the app?
Yeah, that's a common first thought, but unfortunately, it's kind of the road to ruin for reliability.
Mm.
If you put rate limiting on the client side, it's just fundamentally untrustworthy.
Oh, so
Well, think about it. Anyone who's even slightly determined can look at the client-side code, figure out how the limit works, and just bypass it. They can forge requests directly to your servers, completely ignoring whatever limit you tried to set in the app.
right. You have zero control over the client environment.
Exactly. We basically have to operate on the principle of trust no client. Anything outside our own controlled server infrastructure can be manipulated.
Okay, so client side is out. That firmly puts us in the server-side strategy. Control stays with us.
Precisely. And the standard preferred way to do this is either as a middleware component, so some code that intercepts the request before it hits your main application logic,
Oh.
or very commonly these days, especially in microservice setups, you put it inside an API gateway.
Right, API gateway, that term is everywhere. For someone maybe newer to that, can you explain its role? Why is it the natural place for this?
Yeah, think of the API gateway as like the single smart front door for all your backend services. In a microservices world, you might have dozens of little services doing different things. The gateway sits in front of them all and manages how the outside world talks to them.
So it handles more than just rate limiting.
Oh yeah, way more. It typically handles things like SSL termination, HTTPS. It does authentication, checking user tokens or API keys. It can handle request routing, logging, monitoring, IP whitelisting, and crucially for us, rate limiting.
So it's like a bouncer, checking IDs and making sure the club doesn't get too full before letting people in.
That's a great analogy. Yeah.
Yeah.
It acts as this initial checkpoint. It prevents your actual back-end services, the ones doing the heavy lifting, from even seeing requests that don't meet the basic criteria, like authentication or rate limits.
It's a shield, basically.
Yes.
And when it deflects a request because of rate limiting, there's that standard signal it sends back, right? The HTTP 429 code.
That's the key signal, HTTP 429, too many requests. It's the universal, hey, slow down message.
Okay.
So picture this. Your limit is, say, 2 requests per second. A client sends 3 requests really fast.
All right.
The API gateway catches all 3. It checks its counter. It sees the first 2 are okay, sends them through to the backend service. But the third one, the gateway sees the limit is hit. It immediately stops that request right there, sends back the 429.
And the important part is, the backend service never even knew about that third request.
Exactly. It never used any CPU, any memory, never hit the database for that third request.
Yeah.
The rejection happens right at the front door super efficiently.
Okay, so that brings us to a huge choice for any company setting this up. Do you build your own rate-limiting service, maybe as middleware? Or do you use a third-party commercial API gateway solution, like, AWS API Gateway or Kong or Apogee? What are the trade-offs there?
That's a really big decision. It boils down to control versus engineering effort, basically. First thing to look at is your technology stack.
Meaning?
Well, rate limiting needs to be fast, really fast. Is the programming language your team mainly uses, maybe it's Python, maybe Ruby, maybe Java, is it efficient enough to handle this kind of high concurrency, low latency check without becoming a bottleneck itself? If your language is maybe a bit slower, implementing it server-side might actually slow down all your traffic.
If the check takes longer than the actual request processing, you've got a problem.
Precisely. Second factor is algorithm control. If you build it yourself, you have total freedom to choose whichever algorithm works best for your traffic patterns. Token bucket, sliding window, whatever. We'll get into those. But a third-party gateway, they might only offer 1 or 2 basic options, maybe just a simple fixed window, which might not be ideal for you.
So building it yourself gives you more precise control over the behavior.
Definitely. Third, think about your existing infrastructure. If you're already deep into microservices and you already have an API gateway doing authentication, logging, routing, well, adding rate limiting to that existing gateway often makes a lot of sense. It consolidates things.
Keeps related functions together.
Right. And finally, the big one, engineering resources. building a truly robust, highly available distributed rate limiter that scales and, crucially, doesn't fail. That's not a weekend project.
Yeah, I bet.
It takes serious engineering time, expertise in distributed systems, ongoing maintenance, monitoring. If your team is already stretched thin, buying a commercial API gateway solution is often way faster and maybe even cheaper in the long run than dedicating internal engineers to build and maintain it.
So it's that classic build versus buy decision weighed against how much control you really need.
Exactly. How much is that total control worth in terms of engineering investment?
Wow.
Okay, let's get into the real engine room now. The algorithms themselves. Choosing the right algorithm is critical. It dictates how accurate your limits are, how much memory you're going to use, and importantly, whether you can handle sudden bursts of traffic. There are about 5 popular ways to do it, and each has, definite pros and cons.
All right, let's break them down. Where should we start? Maybe the one that's known for handling bursts. ####A. Token bucket, the burst handler, used by Amazon and Stripe.
Yeah, the token bucket is a great place to start. It's really popular, used by giants like Amazon and Stripe, precisely because it's good at handling uneven traffic. Think of it like a bucket.
Okay, a literal bucket.
A virtual bucket, yeah. This bucket has a maximum capacity. That's the bucket size, the max number of tokens it can hold.
And tokens represent allowed requests.
Exactly. And tokens are added to this bucket at a steady preset rate. That's the refill rate, say 10 tokens per second.
Got it. Bucket size, refill rate.
Now, when a request comes in, it tries to take 1 token out of the bucket. If there's a token available, great. The request goes through and 1 token is removed.
And if the bucket's empty?
Request gets dropped or, rejected with a 429. Also, if tokens are added when the bucket is already full, they just spill over. They're discarded. You can't save more than the bucket size.
Okay, so the burst handling comes from the fact that if a user is quiet for a while, their bucket fills up with tokens.
That's the key. If your refill rate is 10 tokens per second and the user does nothing for 5 seconds, they've accumulated 50 tokens up to the bucket size limit. This means they can then suddenly make a burst of 50 requests all at once, using up those saved tokens.
So that's a big pro. Allows bursts of traffic, which is good for things where maybe a user clicks a button and the app needs to make a bunch of API calls quickly.
Exactly. It's also relatively easy to implement, and it's pretty memory efficient. You basically just need to store 2 numbers per user or per key, the current number of tokens in their bucket, and the timestamp of when it was last refilled.
Sound pretty good.
Yeah.
What are the downsides? You mentioned tuning parameters earlier.
Tuning is the main con, yeah. You have those 2 parameters, bucket size and refill rate. Setting them correctly is tricky. Set the refill rate too high, and maybe you let too much traffic through, potentially overloading things or costing more. Set the bucket size too small, and you might block legitimate users during those normal expected bursts, which is a bad user experience.
So it needs careful observation of how people actually use the system.
Right. And another complexity. If you have multiple different limits for the same user, like limit posts per second and friend requests per day and likes per hour, you often need a separate token bucket for each rule, for each user. That can multiply quickly.
Okay, 1 bucket per rule per user. Got it. What's next? ###B3DIA. Leaking bucket, the stabilizer used by Shopify.
Next up is the leaking bucket. If the token bucket is about handling bursts of input, the leaking bucket is more about ensuring a steady output. Shopify is known to use this one.
Okay, steady output, how does it work?
It uses a queue, usually a first-in, first-out FIFO queue, as its bucket. When requests come in, if there's space in the queue, the request is added to the end.
And if the queue is full?
Requests gets dropped, just like the token bucket when it's empty. But the key difference is how requests leave the queue. They aren't processed immediately. Instead, they are pulled from the front of the queue and processed at a fixed, constant rate. Imagine water leaking out of bucket at a steady drip. That's the processing rate.
So it smooths out bursts on the way out.
Precisely. The big pro is that it guarantees a stable outflow rate. This is great if your backend systems absolutely cannot handle sudden spikes in load. It ensures they receive work at a predictable, manageable pace. It's also memory efficient because the queue size is fixed.
Makes sense for stability. But what happens if a huge burst of traffic comes in and fills up that queue?
That's the main con. If a burst fills the queue, those requests will sit there waiting to be processed at that fixed leaky rate. Now, if new requests arrive shortly after the burst,
They get dropped. even if the burst itself is stopped.
Exactly. The queue is full of older requests from the burst, so newer, possibly more important requests might get rate limited simply because the system is still working through the backlog. It can penalize recent requests because of past traffic, and, like the token bucket, tuning that fixed outflow rate parameter requires careful thought.
Okay, so token bucket handles input bursts. Leaking bucket ensures smooth output, but can delay new requests after a burst. What's the simplest approach? ###C. Fixed window counter. The simplest but flawed.
The fixed window counter. This is probably the most intuitive one. You just divide time into fixed chunks like, say, 1-minute windows, 1.0.000 to 1.0.59, then 1.0, 1.00 to 1.0, 1.59, and so on.
Okay, and you just count requests within each window.
Yep. You have a counter for each window, per user, per IP, etc. A request comes in, you increment the counter for the current window. If the counter is below the limit, say 5 requests per minute, the request goes through. If it hits 5, any more requests in that same minute window are blocked.
And then at the start of the next minute,
The counter just resets to 0. Start fresh.
the pros seem obvious.
Yeah.
It's super easy to understand and implement, right? And very memory efficient, just one counter per key per window.
Exactly. It's useful if you have a requirement where quotas must reset precisely at the top of the minute or the top of the hour.
Oh. I remember reading, this one has a big problem. Something about the edges of the windows.
The dreaded edge issue. Yes, this is the major con, and why it's often considered flawed for systems needing accuracy. It allows a burst of traffic right at the window boundaries to effectively double the rate limit.
Can you walk through that example? Let's use the 5 requests per minute limit.
Okay. Imagine the time window is 2.0000 to 2.0.59. A user sends 5 requests right at the end of the window, say between 2.000.55 and 2.000.59.
Okay, those 5 are allowed, the counter hits 5.
Right, now the clock ticks over to 2.01100, new window starts, counter resets to 0. The same user immediately sends another 5 requests, say between 2.01.00 and 2.01.05.
And those are allowed too, because the counter for the new window just started.
Exactly. But look at the actual time period between 2.00.55 and 2.01.05. That's only 10 seconds. But in that 10-second rolling window, the user sent 5 plus 5 equals 10 requests.
Ah, so even though the limit was 5 per minute, they managed to send 10 requests in a much shorter period, effectively double the intended rate just by hitting the boundary.
Precisely. The system is blind to what happened just before the window reset. This inaccuracy means it can allow potentially twice the traffic rate, making it unsuitable if you need strict enforcement.
Okay, that's a pretty big flaw. How do we fix that boundary blindness? #tag sliding window log. The most accurate, but costly.
To fix the boundary issue, we need to move away from fixed windows and think about rolling windows. The most accurate way to do this is the sliding window log.
Log, does that mean keeping track of every single request?
Pretty much, yeah. Instead of just a counter, this algorithm maintains a log, usually a timestamp, for every single request made by a client within the current rolling window duration, for example, the last 60 seconds. This log is typically stored in a very fast in-memory cache, often using something like Redis sorted sets, which keeps the timestamps ordered.
Okay, so you have a list of timestamps for the last minute. How does it decide if a new request is allowed?
When a new request comes in, say at time t, the system first does some cleanup. It removes all timestamps from the log that are older than t minus 60 seconds or whatever the window duration is.
Got it. Prune the old ones.
Then it adds the timestamp t of the new request to the log. Finally, it just counts how many timestamps are currently in the log. If that count is less than the rate limit, say 5, the request is allowed. If it's equal to or greater than the limit, the request is rejected.
So it's always looking at the exact count within the true rolling 1-minute window ending right now.
Exactly. The pro is crystal clear. It is very accurate. It guarantees that the rate limit won't be exceeded in any possible rolling window. It completely solves the fixed window boundary problem.
That sounds ideal. What's the catch? I feel like storing every timestamp must have a cost.
And that's the huge con, high memory consumption. Think about it. If you have a rule allowing, say, 100 requests per minute, you might need to store up to 100 timestamps per user or per key just for that one rule. Now multiply that by millions of users and potentially many different rules.
The amount of memory needed in your Redis cache explodes.
It becomes enormous, yeah. You're storing data for every single request, even the ones that were ultimately allowed and are now just historical data points within the window. For many systems, especially high-traffic ones, the cost of that much fast in-memory storage is simply prohibitive.
Okay, so perfect accuracy, but potentially bankrupting memory costs.
Yeah.
There must be a middle ground. Hashtag techie sliding window counter. The hybrid approximation.
There is, and that's the sliding window counter. It's a clever hybrid approach that tries to get the smoothness and accuracy benefits of the rolling window concept, like the log method, but without that massive memory footprint.
Okay, a hybrid. How does it approximate the rolling window without storing all the timestamps?
It combines the low memory usage of the fixed window counter with the rolling idea. It estimates the count in the current rolling window by using the count from the current fixed window plus a weighted portion of the count from the previous fixed window.
Weighted portion, how does that work?
Okay, let's imagine our windows are 1 minute long and our rolling window is also 1 minute. A request arrives, say, 20 seconds into the current minute window, for example, at 2.01.2 now.
Right.
The current 1 minute rolling window from 2.00.00 to 2.01.20 covers the first 20 seconds of the current fixed window, 2.01.00 to 2.001.59, and the last 40 seconds of the previous fixed window, 2.00.00.59.
Okay, so it overlaps the previous window by 40, 60, or 66.7%.
Exactly. So the formula is roughly count in current fixed window plus count in previous fixed window overlap percentage.
Let's try an example. Limit is 7 requests per minute. We had 5 requests in the previous minute's fixed window. We've had 3 requests so far in the current minute's fixed window. A new request arrives 42 seconds into the current minute.
Okay, 42 seconds in means the rolling window overlaps the previous fixed window by 60, 42, 60 equals 18, 60 equals 30%,
Okay.
0.3. So the calculation is 3 current plus 5 previous, 0.3 plus 1.5 equals 4.5.
So the estimated count in the rolling window is 4.5. Since the limit is 7, this request is allowed.
Right. It gives you a smoother rate calculation that accounts for recent past behavior without needing to store every single timestamp. The pro is definitely that it smooths out the traffic spikes you get with the simple fixed window, and it's very memory efficient. You only need to store the counts for the current and previous fixed windows.
But you called it an approximation. What's the downside? Where can it be inaccurate?
The con is that it is an approximation because it fundamentally assumes the requests in the previous window were evenly distributed throughout that window.
Which they almost never are in reality.
Yeah. Exactly. If all 5 of those previous requests happen in the first second of that previous window, our calculation using the 30% overlap is technically wrong for the true rolling window. However, in practice, does this matter much?
Good question.
Well, people have tested this. Cloudflare published some data saying they used a similar approach. And out of like 400 million requests, the error rate requests that were allowed when they shouldn't have been, or vice versa, was incredibly tiny, something like 0.003%.
Wow. Okay.
So for most real-world applications, that level of minor inaccuracy is usually considered a totally acceptable trade-off for the huge gains in memory efficiency and performance compared to the sliding window log.
Right. It's good enough, basically, and way cheaper.
Pretty much. It hits a sweet spot for a lot of systems.
Okay, so we've explored the algorithms. Let's say we've picked one, maybe the sliding window counter for its balance. Now we actually have to build this thing to work at scale in a distributed system. First question, where do we store the state? Those counters, the previous window counts.
Yeah, the data store choice is crucial. We need speed, like single-digit millisecond speed for reads and writes. Using a traditional database like PostgreSQL or MySQL, that writes to disk, forget it, it's way too slow. The disk access latency would kill performance.
So it has to be in memory.
Absolutely. The standard choice here is an in-memory cache, and the most popular one for this job is Redis.
Why Redis specifically? What makes it so good for rate limiting?
Well, besides just being incredibly fast because it keeps data in RAM, Redis has a couple of commands that are almost perfectly designed for rate-limiting algorithms. First is incr.
Increment.
Yeah, it lets you atomically increment a counter value stored under a key. Atomically is a key word there. It guarantees that the increment operation happens as one indivisible step, which helps avoid race conditions, which we'll get to.
Okay, atomic increment. What else?
The second crucial command is expire. This lets you set a timeout, a time to live, on any key in Redis. So for our window counters, we can say, increment this counter and make it automatically disappear in 60 seconds. Redis handles the cleanup for us. It's perfect for managing those time windows without needing extra cleanup logic in our application.
Okay, Redis seems like the perfect tool. Fast atomic increments, automatic expiration. But as soon as we scale this out, running our rate limiter logic on multiple servers to handle the load, we hit that classic distributed systems problem. Race conditions.
Yep. This is where things get subtle and can break easily if you're not careful. Let's look at the basic steps our rate limiter logic takes. 1. Read the current counter value from Redis. 2. Check if incrementing it would exceed the limit. 3. If not, increment the counter and write it back to Redis.
Okay, read, check, write. Seems simple. Where does it go wrong with multiple servers?
Okay, imagine the limit is 5 requests. The current counter value in Redis for a specific user is 3. Now, 2 requests for that same user arrive at almost the exact same time, but they hit 2 different rate limiter servers, server A and server B.
Okay, concurrent requests.
Server A reads the counter, value is 3. Server B reads the counter, value is also 3. Both servers now do the check. Is 3 plus 1, which is 4, less than the limit of 5? Yes, it is.
So both servers think it's okay to proceed.
Right. So server A increments the value to 4 and writes it back to Redis. Then server B also increments the value at red, which was 3 to 4, and writes that back to Redis, potentially overriding server A's write.
Whoa, so the final value in Redis is 4.
Hmm.
But 2 requests actually got through. The count should be 5.
Exactly. The race condition meant we allowed an extra request through because the read, check, write sequence wasn't atomic across the 2 servers. The limit was violated.
How do we prevent that? Locks.
You could use locks, but traditional distributed locking mechanisms can be complex to manage and often introduce significant performance bottlenecks. They slow things down, which is exactly what we don't want in a rate limiter.
So what's the better way in a Redis world?
The common, elegant solution is to use Redis's built-in scripting capabilities, specifically with Lua scripts.
Lua scripting, how does that help?
Redis allows you to send a script, written in Lua, to the server. Redis guarantees that it will execute that entire script atomically. So you can write a small Lua script that does all 3 steps, read the current value, check the limit, and conditionally increment write the new value all inside that one atomic operation on the Redis server itself.
Ah, so Redis handles the atomicity. No other command can interfere while that script is running for that key.
Precisely. It moves the critical read, check, write logic directly onto the data store, ensuring it happens without interruption and preventing the race condition entirely. It's a very common pattern for reliable distributed counters.
Okay, race conditions solved with Lua. What's the next big challenge in a distributed setup?
Synchronization. Remember, we have multiple rate limiter servers, or pods or instances, and clients like web browsers or mobile apps are usually stateless. A user might hit server 1 for their first request, then server 2 for their second, server 3 for their third, just based on load balancing.
Right, so server 2 doesn't know what happened on server 1.
Exactly. If each server tried to keep its own local count in its own memory, they'd be completely out of sync. Server 1 might track 3 requests for user X. Then user X hits server 2, which thinks the count is 0. User X could easily bypass the limit by just spreading requests across different servers.
Could we use something like sticky sessions where the load balancer always sends user X to the same server, say server 1?
That's generally considered the rejected solution for high-scale resilient systems. Sticky sessions make load balancing harder, they reduce fault tolerance. If server 1 goes down, all users stuck to it are out of luck, and they make deployments and scaling much more rigid.
So no sticky sessions. What's the accepted way?
The accepted solution is why we chose Redis in the first place, a centralized data store.
So all rate limiter servers talk to the same shared Redis instance or cluster to get the counts.
Exactly. Redis becomes the single source of truth for all counters. When server 1 processes a request for user X, it increments the counter in the central Redis. When server 2 gets a request for user X a millisecond later, it also checks the same central Redis, sees the updated count, and makes the correct decision.
But doesn't having one central place introduce its own bottleneck?
Yeah.
Or a single point of failure?
That's the inherent trade-off, yes. You centralize the state to solve synchronization, but you accept the dependency on that central store. That's why making Redis highly available using clustering, Sentinel, replicas, and ensuring network connectivity is lightning fast is absolutely critical. The speed of Redis usually means the check itself is sub-millisecond, making the bottleneck manageable for most workloads, and it's the necessary price for achieving consistency.
Okay, central Redis is the key for synchronization. Now, how do we actually define all these different limits? We talked about posts per second, logins per minute per IP, etc. Where do these rate limiting rules live?
Typically, these rules are defined in configuration files. Think YAML or JSON files, stored on disk, or maybe in a central configuration service. They need to be really granular to handle complex scenarios.
Can you give an example of what OR rule might look like in a config file? You mentioned list system earlier.
Yeah, they often use a structure with domains and descriptors. For example, you might have a rule like
Messaging.key.
Yeah.
Message type value.marketing.key.userit.
5 per day.
Okay, so that limits marketing-type messages to 5 to user per day.
Exactly. Or for security.
Off.key.action.value.login.attempt.key.IP address
5 per minute.
limits login attempts to 5 per IP address per minute. That's quite flexible.
Very. So the overall flow looks something like this. Your deployment system pushes these config files out. Worker processes on the rate limiter servers, or API gateway, read these rules from disk and maybe cache them in local memory for speed. When a request comes into the middleware or gateway, it finds the matching rule from its local cache based on the request properties, user ID, IP, API endpoint, etc. Then it constructs the unique key for Redis, for example, ratelimit.auth.loginattempt.1.2.3.4. It calls Redis, using that Lua script, to check and increment the counter for that key based on the limit defined in the rule, 5 per minute.
And Redis gives back the current count or signal if the limit was hit.
Right. Based on Redis's response, the middleware either allows the request to proceed to the backend service or immediately returns that 429 too many requests error. It's this constant rapid-fire cycle. Check local rules, check central state in Redis, make decision.
Okay, so the primary action when a limit is hit is returning that HTTP 429 error.
Mm-hmm.
But you mentioned earlier, what if it's a really important request, like placing an order during a big sale? Just dropping it seems harsh if it's just temporary overload, not malice.
That's a great point, and the action really depends on the context and the value of the request. For high-value, state-changing requests like submitting an order or maybe a critical background job, dropping it is often unacceptable. The alternative is to enqueue the request.
Meaning?
Instead of immediately rejecting with a 429, the rate limiter or API gateway can put the request into a reliable message queue, something like Kafka or RabbitMQ or SQS. The request waits in the queue, and backend worker processes can pull requests from the queue and process them at a sustainable rate as resources become available.
So it still protects the back end from overload, but it doesn't lose the user's request. It just delays processing.
Exactly. Dropping 429 is usually for things you suspect might be abuse or less critical operations. Queuing is for handling temporary, benign overload for requests you absolutely must process eventually.
That makes sense. Now, for the requests that do get the 429, how do we make that experience better for the client, the developer, trying to use the API? They need to know why they were blocked and what to do next. This is where those HTTP headers come in, right?
Absolutely critical for a good developer experience. You shouldn't just send a 429 status code alone. You need to provide context using standard HTTP response headers. And ideally, you should send some of these headers on successful responses too, so clients can see limits approaching.
Okay. What are the key headers?
There are 3 main ones. First, X rate limit.
And that tells the client.
The total number of requests they're allowed within the current time window. Like, your limit is 100 requests per hour. It sets the baseline.
Okay. Second header.
X rate limit remaining. This tells the client how many requests they have left in the current window. So after they make one request, the response might say X rate limit remaining, 99.
So clients can actually track their usage and maybe slow down proactively before they even hit the limit.
That's the idea. It allows for smarter client-side behavior. And the third header, which is absolutely crucial when you do return a 429 error, is X rate limit retry after.
Retry after. That sounds important.
It is. This header tells the client exactly how many seconds they must wait before attempting another request. It might say retry after 30. This isn't just a suggestion, it's basically an instruction. It stops clients from just hammering the API immediately after being blocked, which would just make the overload worse.
So these headers turn a frustrating error into something more predictable and manageable for the client developer.
Precisely. Good API design includes good communication about limits.
Okay, let's talk performance optimization. We need this rate limit check to be incredibly fast, especially at global scale. Latency is the enemy. How do we minimize the delay added by the check?
The main strategy is reducing physical distance. You need to use multi-data center setups for your rate limiter logic and, importantly, for your Redis clusters, and you leverage edge computing.
Edge servers, like CDNs.
Similar concept, yeah. Services like Cloudflare, Fastly, or cloud provider edge locations. The research mentioned Cloudflare having something like 194 edge locations worldwide. The idea is to route the incoming user request to the geographically closest edge server. That server can then perform the rate limit check, talking to a nearby Redis instance if possible.
So you minimize the round-trip time between the user, the checker, and the counter data.
Exactly. Keeping those components close together geographically is key to shaving off milliseconds and keeping latency low.
But wait, if we have Redis clusters holding counters in London, New York, and Singapore, how do we keep the count for user X consistent across all of them instantly? If they hit London, then immediately hit Singapore, won't there be a delay in synchronization?
Ah, yes, the data consistency challenge across regions. Perfect global, instantaneous consistency is extremely hard and usually very slow. For rate limiting, we typically accept an eventual consistency model.
Eventual consistency.
Yeah, it means we accept that for a very short period, the counter value for user X in Singapore might be slightly stale compared to the value just updated in London. There might be a tiny window, maybe milliseconds, where a user could potentially sneak in one extra request globally because the update hasn't propagated everywhere yet.
So we trade perfect, immediate consistency for lower latency.
Generally, yes. For rate limiting, where windows are often short, seconds or minutes, that tiny potential inaccuracy from eventual consistency is usually considered an acceptable price to pay for the significant performance gain of not having to wait for global synchronization on every single request check. Trying to enforce strong consistency across continents would add massive latency.
Makes sense. Okay, so the system is built, deployed globally, optimized for latency. What about after launch? Monitoring and iteration must be ongoing, right? You can't just set it and forget it.
Absolutely not. Continuous monitoring is vital. You need to collect analytics. Are the rules actually effective? For example, are you seeing lots of 429 errors? Where are they coming from? Are they mostly anonymous IPs suggesting bot traffic or DDoS? Or are they coming from authenticated users?
And if they are coming from real users?
If you see a high rate of 429s from legitimate authenticated users, that's a strong signal your rules might be too strict. You might be blocking valid activity and hurting the user experience. You'd need to analyze that traffic pattern and potentially relax the limits for those specific actions or user types.
Okay, so monitoring helps tune the rules. What about the algorithm choice itself?
You also need to monitor if the algorithm is effective for your traffic patterns. Let's say you chose the leaking bucket for its stable output, but then you run a massive flash sale and your system grinds to a halt or latency spikes because the leaking bucket just can't handle the legitimate burst of traffic. That monitoring data tells you, okay, for this specific scenario, leaking bucket was the wrong choice. You might need to switch to something like the token bucket, which is designed for bursts, at least for the parts of your API affected by the sale. It's an iterative process of observing and adjusting.
Right, always learning from the data. Before we wrap up, let's touch on a few bonus talking points that add a bit more nuance.
Sure. One quick distinction is hard versus soft limiting.
What's the difference?
A hard limit is strict. If the limit is 5, the 6th request is immediately blocked, period. A soft limit might allow a small, temporary overshoot. Maybe the limit is 5, but the system allows up to 7 requests for, say, 10 seconds before the hard block kicks in at 5 again. It acts like a small buffer, potentially providing a slightly smoother experience during very brief spikes.
Okay, a bit of temporary flexibility, and we've focused entirely on rate limiting at the application level, right? Layer 7.
Yeah. Mostly, yes. Handling HTTP requests using 429 codes. But it's important to remember this is a layer differentiation. Rate limiting can, and often should, also happen at lower layers of the network stack.
Like where?
Like at the network layer, layer 3, based purely on IP addresses. You can use tools like iptables on Linux servers or cloud provider firewall rules like security groups or network ACLs to block traffic from IPs generating absurdly high volumes of connection attempts or packets.
So that's a cruder, earlier filter.
Exactly. It's a cheaper way to block obvious high-volume floods before they even reach your more sophisticated and more expensive application layer rate limiter or API gateway. It's defense in depth.
Makes sense. And finally, flipping it around, what about advice for our listeners who are clients of APIs? How can they be good citizens and avoid being throttled unnecessarily?
Yeah, good client behavior helps everyone. First, use client-side caching where possible. Don't repeatedly ask the API for data that hasn't changed. If you fetched user profile info 5 seconds ago, cache it locally instead of asking again immediately.
Okay, reduce redundant calls. What else?
Handle errors gracefully. Your client code should expect 429 errors and recover gracefully. Don't just crash the app. Implement retry logic.
But the retry logic needs to be smart.
Right. Crucially, When you get a 429, you must check for that X rate limit retry after header we talked about. If the server says wait 30 seconds, then your retry logic needs to actually wait at least 30 seconds. This is called implementing exponential backoff or honoring the retry after value. Just immediately retrying after being blocked is the worst thing you can do. It just contributes to the problem and might get your client blocked entirely.
So cache aggressively, handle 429s, and back off properly when told to.
That's the essence of being a well-behaved API client. Hashtag tag 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 outro.
Wow, okay, that was definitely a deep dive. We've journeyed through, well, the whole life cycle, really, starting with why rate limiters are so crucial, stability, security, cost control, then figuring out where to put them, that server-side versus client-side decision, and the role of middleware or API gateways.
Yeah, and then we really got into the weeds with the algorithms, didn't we? Breaking down the pros and cons of the token bucket for bursts, the leaking bucket for steady flow, the simple but flawed fixed window, the super accurate but costly sliding window log, and that practical hybrid, the sliding window counter.
It really hammers home that building one of these isn't about finding the single right answer, is it? It's a whole series of informed trade-offs. You're constantly balancing accuracy against memory cost, burst handling against complexity.
It truly is a masterclass in engineering compromise, yeah. Finding the right balance for your specific needs, your scale, your budget.
Definitely. So for the final provocative thought we want to leave you, the listener, with, it connects back to that client-server interaction we just touched on. We spent a lot of time talking about the server sending those headers. X rate limit remaining, X rate limit retry after.
Right. So consider this. How sophisticated do modern client applications need to be? The really well-designed ones aren't just passively receiving those headers, they're actively parsing X rate limit remaining on successful calls. They're watching their own usage approach the limit.
So they can self-regulate.
Exactly. They can proactively slow down their own request rate before they even hit the 429 error based on the information the server is giving them. This turns throttling from being just an error condition into, well, almost a cooperative mechanism. The client and server work together using those headers to manage traffic flow and keep the user experience smooth, even under load.
That's a really interesting perspective. The client becoming an active participant in rate limiting, not just a victim of it.
Yeah.
Food for thought.
Definitely.
Okay, that wraps up this deep dive into the intricate world of rate limiter system design. Thanks for joining us. Until next time, keep digging into the details.